This is one of a series of lectures produced by the Further Mathematics Support Programme to help with A-level revision. This particular lecture is looking at the Edexcel Decision Maths 2 specification, and the topic is allocation problems. The specification talks about the idea of a cost matrix and then the reduction of the cost matrix, and then the Hungarian algorithm to find least cost allocation. So below is a typical sort of example of a cost matrix. When it says cost, it may be in terms of money, but it may be in terms of time or anything else for that matter. But we simply talk about cost for convenience. The matrix reduction is a process which first of all looks at the rows and from each row subtracts the least element. So in the row for H we'd be subtracting 1 from every element in that row. For J, 2, L, 1 and S, 2. Once the rows have been reduced, turn our attention to the columns, and again subtracting the smallest value from each column from every element in that column. Now 3 of the columns already have zeros in, so they're not going to change. So it's only the second column here which will change, and that will have 1 subtracted from every element. What we'd now like to do, if possible, is to allocate each row and each column with a 0, but only 1 0 appearing in each row and 1 in each column. Now in this case it's not going to be possible, because if you look at column 1 we could allocate a 0, but if we allocated S1 for example, then we'd also have to use L1, but that would give us 2 zeros in the first column. Now we don't have to search around blindly. There is a test which allows us to decide whether this is going to be possible at all. That is done by drawing lines across the zeros. Now we need to do that with the minimum number of lines possible. So in this case, a line through the first row, a line through the first column, and a line through the second row covers all of the zeros. If the minimum number of lines required is less than the number of rows and columns, i.e. in this case 4, then an optimal solution can't be found with zeros at the moment. So we move on to the next stage of the algorithm, which allows us to change the values in the matrix by the following steps. We look first of all at the uncovered elements and find the smallest value. In this particular case the smallest value is 1. For that value we subtract 1 from the uncovered elements and we add 1 to the intersection. So we're going to subtract, in this case from all of these, just 1 from each one, and we're going to add where there's an intersection of lines. That produces the matrix that I've got above, and we now proceed again to look at the line test. How many lines were required, or the minimum number of lines required, to cover the zeros that appear in the new table. We can see now there are going to be 4. Once we've decided there are 4, that means an optimal solution can be found, and for example we could allocate S1. Of course now instead of L1, which we would have had to do before, we've got the option of using L2. We could then have J3 and H4. For the actual costs associated with that allocation, we go back to the original table and mark in the same pattern. There are other possibilities, of course. We could have chosen L1, and then that would have meant that S4, which would have meant that H has to do 2, but we could leave J doing 3. And if we look at the first table, then the pattern here written on and you'll notice that the cost of both of those different allocations is the same. They're both equal to 8 units in total. One or two complications which might be put into questions. First of all, the idea of an unbalanced problem. This is where the number of rows and the number of columns don't match. So here we've got 4 rows but only 3 columns. In either of these cases, you simply add in the extra column or row which is required to balance the table, and in there enter zeros. The Hungarian algorithm that we've been talking about is one which minimizes the cost. However, we can adapt things. If we wanted to maximize, then we can do exactly the same process once we realize that maximizing something is the same as minimizing the negative of the table. Now, so what we do is change all of these values to negative and then add on sufficient to make the numbers in the table greater than or equal to 0. This is equivalent to subtracting every number from the largest in the table. So here, if we take the largest, which is 9, and subtract every element from 9 and write it in here, we get the following. The first row will be 6, 8, 5, and 3. And completing that process produces a new table, as you see below, and all we need to do now is to minimize the costs associated with this table. So we can use the Hungarian algorithm as in the first example. Okay, here's an exam question from June 2010. So reading through, first of all, we have a team of 4 workers, Harry, Jess, Louis and Saul, and they're to be assigned 4 tasks, 1, 2, 3 and 4. And each worker must be assigned 1 task, and each task must be done by just 1 worker. It says Jess cannot be assigned task 4, and the amount in pounds that each person would earn while assigned to each task is shown in the table. So this is our cost matrix. In fact, this time it's one which we're looking at earnings. And the question asks us to reduce rows first, use the Hungarian algorithm to obtain an allocation that maximizes the total amount earned by the team. And we must make our method clear and show the table after each stage. And it says state who should be assigned each task and the total amount earned by the team. So the first thing to note is that we're asked to maximize. And the other thing is that we've got a situation where Jess doesn't do task 4. Right? So what we want, if we're trying to maximize, is to put a value in there, which means that Jess isn't going to be assigned that at all. So we want something which is less than everything else. So let's make it 0 in there, and then we'll proceed with that table to use the algorithm to find our solution. Well, the first stage in the algorithm, because it's a maximizing problem, is to subtract everything from the largest value. The largest value is 27. That's L3. So that one is going to be 0 when we subtract from 27. Going through doing that for each one in turn, the top row becomes 9, 3, 5, and 10. And then we do that for each row in turn. The question specifies that we should use row reduction first. So remember that what we need to do then is to look at each row in turn and subtract the smallest element that we have from each of the elements in that row. So in the first row, the smallest is 3. So subtracting that from each of those, 6, 0, 2, and 7. And continuing down the list, the next one becomes 5, 0, 3, and 25, because the smallest element was 2. The smallest element in the next row is 0, so that's not going to change. And then finally, subtracting 1 gives 7, 0, 3. And that final element in there, S4 there, should be 13. So that when we subtract that 1 from there, we end up with a value of 12. So there's a slight error in that position there. Another small error there. Element J2 should of course be 6. 8 take away 2. Now doing a similar thing for the columns, so taking the smallest number from each column in turn. The smallest number in the first column is 2, so taking that away we get 4, 3, 0, 5. Next column has got zeros in it, so that's not going to change, because when we subtract 0, of course, there's no change. And likewise for column 3. The smallest value in column 4 is 5, so when we subtract that, we end up with 2, 20, 0, and 7. So that process is straightforward enough, but do watch out for arithmetic errors. As you've seen, they quite easily can creep in if you're not careful about it. So keep checking your working as you're going through this. And the next stage of the algorithm then is the line test, and it might appear that we're going to require quite a few lines here. However, remember it's the minimum number required that you need to find, and we can find that by placing a line through row L, I beg your pardon, and then one through column 2, and you see that only 2 lines are required in total. So we're not going to be able to find an optimal allocation at the moment. So we need to go on to the next stage of the algorithm, which says look at the smallest uncovered element. In this particular case, the smallest uncovered is 2. And from each uncovered element, subtract that amount. So if we go up to the table up the top now, just looking at the uncovered elements and subtracting 2 from each of those. So we get 2, 0, 0, 1, 4, 18, and then in the final row, subtracting 2 from that, That's 3, 1 and 5. We add 2 to the intersection point. So the intersection is at L2, that's 5. And all other ones, that's those covered just by a single line at the moment, remain the same. So the 0, 0, and they all happen to be zeros in this case. Now, of course, you don't have to use color coding that way, but hopefully you'll see where those different things have happened. The uncovered ones, the blue elements there, have all had the same amount 2 taken from them. The intersection, which is the red one, has had 2 added to that, and the others have remained the same. We now go look at the line test again. And although the number of lines is increased that we need, it is still only 3. So 1 along the top, 1 in row 3, and 1 in column 2. So again, we've got a situation where we're not going to find our optimal solution. So we go through that procedure of changing the size by looking at the smallest uncovered element. In this case, it's equal to 1. So we subtract that from those that are uncovered. 0, 3, 17, and then in the bottom row a 2, 0 and 4. We add 1 to the intersections. This time there are 2 intersection points. And the others remain the same. So 2, 0, 0, 0, and 0, 0, 0. Well, now 4 lines are required to cover up the 0, so we can find our optimal allocation. There's more than one possibility, but for example, we could use J1. If we use J for 1, then S must be doing 2. L could be doing 3, or H could be doing 3. It doesn't really matter. So let's go for H doing 3 and L doing 4. So as long as you get an allocation which satisfies the criteria that each person is doing 1 task and that there's zeros in there, then that's okay. We copy that pattern onto the original table at the top. And then we have to then fill in the table in the answer booklet. So here at the bottom, we've allocated Harry task 3, Jess task 1, Louis task 4, and Thor task 2. And we're maximising, and these are the payments associated with those: £22, £20, 22, and 26, so that the total is £90. The allocation of marks for this was that at each stage 2 marks, method and accuracy marks, were allocated. So the first part, realizing that you were realizing that you were maximizing and had to subtract from 27, first of all was got the first M1A1. The row and column reduction, getting down to this stage, produced A1M1. Following through that again and doing the changing of the matrix by the smallest uncovered element, again M1A1, and doing that a second time, M1A1. So the 8 marks getting down to our final pattern. And then there are 2 marks allocated for the solution at the end to the problem, M1 and A1. One further thing that you might be asked to do is to formulate an allocation problem as this for a linear programming solution. This question illustrates that. So here we have 3 workers, B, Q and R, to be assigned tasks A, B and C. And each worker must be assigned just 1 task, and each task must be assigned just 1 worker. The table shows us the situation and the costs involved in using each worker for the task. And we're trying to minimize that, that cost. So it says formulate the above situation as a linear programming problem, defining your decision variables and make the objective and constraints clear. So we start off by a definition then, and we say something along the lines of let xij be the fact that worker in row I does task J, or is allocated task J. And then xij will be equal to 1 if the task is allocated, and equal to 0 otherwise. The objective is to minimize the total cost, and the total cost is calculated by the value in each cell. So for example 27 is in the first cell in row 1 column 1, so it will be 27 multiplied by x11 plus 31 is in row 1 column 2, and then 25 is in row 1 column 3. So that's the first row, and of course depending on whether x11, x12 or x13 is equal to 1 or 0, then that will give us the cost associated with the particular allocation. We do that for each row in turn, so adding them all up as we go along. So 26 x21 plus 30 x22 plus 34 x23, and the final row 35 x31 29 x32 and 32 x33. The constraints that we have are that the total in each row and each column must be equal to 1. So there must be 1, 1 and the others are 0. So the total, the sum of each row and column is equal to 1. So the sum of 1j from 1 to 3 for j equal to 1 to 3, that's the first row. The sum in the second row, j equal to 1 to 3, is equal to 1, and the sum in the third row, x3j, is equal to 1, and that's from j equals 1 to 3. Similarly, the sum in the columns, now the columns are xi1 from I equals 1 to 3. The sum from I equals 1 to 3 of the second column, that's xi2, That's 1. And finally, the sum in the third column is also equal to 1. So those are the constraints. That's the idea that each column and each row has exactly 1 1 and the others are zeros. That's the end of this lecture on allocation. Lectures for other modules and other topics in the Decision Maths 2 can be found via www.furthermaths.org.uk.